This is going to be the first part of a series of recordings about the complex numbers. And I want to begin by just thinking out loud a little bit about how we usually learn about complex numbers and imaginary numbers in school. For most of us, our first encounter with imaginary numbers is as solutions to the equation x squared equals negative 1. In other words, we know that x squared equals negative 1 has no solutions in the real numbers. So what we do is we pretend. We just say, well, let's suppose that there is a number that's the square root of negative 1. We'll call that number I. And then we're going to say, well, if that thing did exist, we're just going to pretend it exists. And then we can consider all kinds of numbers you can build out of that. Like, for example, you can take a combination of real numbers and multiples of I. And so we end up studying properties of the complex numbers. So most high school students first encounter this approach in the context of Algebra 2, and they learn, it comes up typically from the study of the quadratic formula. So this approach is very reasonable pedagogically, but one big problem with it conceptually is that it casts the entire theory of complex numbers as basically a fake. Like, we're just pretending these things exist. They don't really exist. We're going to talk about what would happen if they did exist. But everything is in this kind of hypothetical, let's believe, let's pretend kind of zone. And all of it then seems to be completely disconnected from reality. And of course, we use the words real numbers and imaginary numbers, which just completely solidifies that sense that all of this is, in a sense, totally disconnected from anything to do with reality. And logically, anything that follows from a premise that is known to be false is a conclusion that's unreliable. And so you could argue that this whole approach is building a theory of complex numbers on a foundation of lies. And then what do you do with that? What value does that have? So there's another approach to complex numbers, and I'm going to talk you through that approach now. So the second approach to complex numbers was first developed by Hamilton, William Rowan Hamilton, in the, I want to say, 18th century. And Hamilton was the mathematician who invented what we now would call vectors. And this approach may be familiar to many of you, perhaps not. I'm going to run through it as quickly as I possibly can. The idea that Hamilton had was to think about not numbers, single real numbers, but about pairs of real numbers. So consider a pair of real numbers. We would use the language ordered pair. Try again. Consider a pair of real numbers a comma b. You can think of a comma b either as a point in the plane, or you can think of it as a vector. That is to say, A indicates a horizontal displacement and B indicates a vertical displacement. And we start talking about how one adds vectors. So there's a vector addition operation, which is, of course, defined component-wise. So you add the x components and you add the y components, and this corresponds geometrically to addition of vectors. So if you go 3 units to the right and 5 units up, and then you go 2 units to the right and 6 units up, you can find out the total displacement by adding the horizontal components and adding the vertical components together. It makes perfect sense. There's also a scalar multiplication operation, where you take a pair and you multiply it through by a real number. And you can think of this then as taking a vector and just stretching it out by some scale, which is why it's called a scalar. It stretches things, right? So we've got these two operations. And to these two operations, Hamilton added a third operation, a multiplication of vectors. And this is the probably strange part. So Hamilton's vector multiplication was defined by taking a pair AB and a pair CD, and the product of those two pairs is given by AC minus BD, comma, AD plus BC. Now, this definition of multiplication is admittedly very non-obvious. There's no reason one would expect this multiplication operation to be useful in any way. But what Hamilton was able to show was that this multiplication law has some really nice features, and I want to take you through what those features are now. So the first really useful feature of this multiplication law is that it is commutative, it is associative, it distributes over multiplication, over addition, I should say. So that's three pretty important properties. There is an identity element in it. You can verify for yourself that 1, 0 times any other vector just gives you back the other vector. So that's nice. And another really nice feature about this multiplication law is that elements of the form r comma 0, when you multiply them together, two elements that have a 0 in the second component, you just end up getting the product of rs comma 0, just like this. And of course, when you add elements like that, it goes without saying that you just end up getting the sum in the first component and the 0 in the second component. And so what this means is that if you think of r comma 0 as being sort of a renamed version of just the real number r, you can think of the entire real number line as sitting on the x-axis of the plane. And when you take any two numbers on that x-axis, and you just think of them as real numbers, and you multiply them together, or you add them together, or you do whatever you want to do with them, you end up getting the same result, whether you think of them as just real numbers, or whether you think of them as numbers, as pairs of numbers, points on the plane, with this Hamiltonian kind of complicated multiplication law. So along with that, another nice feature that's easy to overlook is that if you take a number on that x-axis, a number like r0, and you multiply it times any other point on the plane, like AB, you end up getting RA comma RB. You can check this yourself. It follows from the multiplication law that Hamilton used, which means that it's the same result that if you had just taken the real number AB. The real number r and multiplied it times AB. So, in other words, this complex multiplication, and that's what I'm going to call it from this point on, it's complex in the sense that it's a rather complicated formula. This complex multiplication is completely compatible with scalar multiplication. And the real line embeds in the plane. So you can think of this multiplication law as defining an extension of ordinary multiplication into a two-dimensional world. And the last important thing about this multiplication law is that if you consider the point 0, 1, and you multiply it times itself. So remember, Hamilton's multiplication law says it would be 0 times 0 0 times 0 minus 1 times 1, so we end up with a minus 1 in the first component, and then for the other components you just get 0. And that matches up with the number -1, according to this association we're using, where points on the x-axis correspond to points on the number line. So the equation x squared equals -1 has a solution in this two-dimensional system that we're in. There's all kinds of other lovely features you can find. It turns out, and I'm not going to prove this now because we're going to return to this later on, every non-zero element, every pair AB where they're not both 0, has a multiplicative inverse. That's certainly not obvious from the definition, but it turns out to be the case, so this is a field. And the last thing to note is that within this notation, any vector of the form AB can be written as A0 plus 0b. Of course, that's just vector addition. And since we have scalar multiplication, you can rewrite those as A times 1, 0 plus B times 0, 1. And this is, of course, the multiplicative identity. It's just 1, and so you can just write that as a times 1. And this is that element whose square is equal to -1. We're just going to call that I from now on. And so we end up with the complex numbers. But the difference between this approach and the first approach I spoke about at the beginning of this recording is that we're not pretending that there are solutions to x squared equals -1. We're not indulging in some kind of imaginative exercise where we say, well, what if there were square roots for negative numbers, and then we start playing with those square roots. We're actually constructing out of real components a number system in which there are square roots for negative numbers. We don't have to pretend anything. We're just designing a new kind of number system that has exactly the properties we want. And as long as you're willing to think of these two-dimensional points as being sort of like a generalized number system that contains the real number system within it, that's really important, then everything is totally consistent when we end up reconstructing the complex numbers just like we want them to. Now, this approach also has a downside, and it's perhaps obvious to you at this point what that downside is. It has to do with that multiplication law, which I will write down again for your reference. When Hamilton decided that AB times CD was going to be equal to AC minus BD, comma, AD plus BC, this formula seems to come out of nowhere, right? And so we've replaced the, we've done away with the kind of imaginary, let's pretend quality of the complex numbers, but at the cost of what seems to be a totally unmotivated and completely arbitrary formula. Now, in hindsight, this formula works great, and I'm sure you know that there's all kinds of geometric interpretations that go along with this. For example, you can think of multiplication of vectors as involving a combination of a rotation and a stretch, and I'm sure you know all about that stuff. But this formula, AC minus BD, comma, AD plus BC, doesn't seem intuitively to have any kind of logic to it. It really is only justified after the fact. And we know that there are other formulas that seem much more natural. For example, we have considered the possibility in previous classes of defining multiplication of vectors component-wise. So what if you just define AB times CD in the natural way, AC, comma, BD? This is a different multiplication law, right? If we want to call Hamilton's law complex multiplication, we can call this multiplication law direct multiplication. And the nice thing about direct multiplication is, of course, it is commutative. We've established this before. It's associative. It distributes over addition. It has all of those nice properties. It has an identity element. The identity element is not 1 comma 0, it's 1 comma 1. But that's okay, it's just a different identity element. So we have a ring, right? We have a multiplicative structure that's compatible. We can also note that real numbers, so you can take a real number C, and if you just associate it with the ordered pair C comma C, that would be a multiple of 1 comma 1, multiples of the identity. We end up with an embedding of the real numbers in the plane, just like we do with complex numbers. So what you can think of is we have our two-dimensional plane, and then points along this line. This is basically the real line, plopped inside of the plane, but at a 45-degree angle to the axis. And you know, you take any 2 points on this plane. It doesn't matter whether you think of them as ordinary real numbers or whether you, take any 2 points on this line, on this 45-degree line. It doesn't matter whether you think of them as just real numbers or whether you think of them as pairs of numbers. The multiplication law treats them the same way. So if you take CC and you multiply it times DD, you end up with CD, comma CD. And it also is the case that if you take a real number RR and you multiply it times AB, it just acts like scalar multiplication. Right, so all of the nice properties that we talked about for complex multiplication also seem to work here with two important exceptions. And one important exception is that we have these non-invertible elements. So any element of the form a comma 0 or 0 comma b is going to end up being non-invertible with this multiplication law. So we don't have a field, and that's an important difference between the direct product and the complex product. The direct product has non-invertible elements in it. And the other interesting thing about the, not only is this not a field, it's not even an integral domain, because any element of the form a0 times 0b is going to give you just 0, the additive identity. So we're dealing with a ring that is not an integral domain. Okay, so fine. So we have these two examples, two different ways of defining a product on the real plane. So you can define the product the way Hamilton did, which is, I'll just write this down again, AC minus BD, comma, AD plus BC. And that gives you a complex set of numbers, and it's a field. Or you could define A, B, C, D in the most natural and obvious way to do it. And this gives you the direct product. It's not an integral domain. Okay, well, so now we know there's two types of products, but I mean, is that all? And so one could ask the question, are there other products you could define, and what kinds of nice structures would those give you? And so what I'm going to do now in the next part of this set of recordings is take you through a theory of a complete classification system for every single possible product. It turns out there are infinitely many different products you can define on the real plane. However, all of those products can be classified into one of three types. One type of them is basically the same as the complex numbers. The second type of them is basically the same as the direct product. And the third type of them is basically the same as a third kind that I haven't talked about yet. So the things we're going to need to do are figure out what I mean, first of all, by basically the same, and how you can take the incredible variety of every single possible multiplication structure on the real plane and distill it down to a three-part categorization. And that's what I'm going to do in the next part of this recording.